Hi, my name is Jacob Pushy, and today I will be discussing with you the Module 5 Advanced Concept presentation topic. Cellular respiration is the process that allows your body to harvest a huge amount of energy from a single glucose. In fact, as we've learned in the description of this project, it is so efficient that you get 30 ATP for every one glucose molecule you eat. This exercise that we're doing here in this presentation is going to break down exactly where each ATP comes from. For this presentation, I was instructed to walk you all, the audience, through every step involved in generating an ATP, NADH, and FADH2, and include the names, structures, and enzymes for each step. From there, I sought to understand the conversion rates from NADH and FADH2 to ATP, and then calculate how 30 ATP are formed. In addition, I included any step which uses an ATP. Firstly, what is cellular respiration and why is it important? Cellular respiration is the combustion of fuels into CO2 and H2O to generate ATP. This is an aerobic process, and it takes place in the mitochondria. This process is defined by two parts, the citric acid cycle and the oxidative phosphorylation. So here I will show you this process, the respiration, aerobic and anaerobic pathways. So we'll look starting in this area, kind of the beginning portion. So glycolysis generates 4 ATP molecules of ATP per molecule of glucose. So here is that chain there. And then here is this and this, which will supplement that. So if we look further at the anaerobic process here, sorry guys. So here we're going to look at the anaerobic process. If we look here further at the anaerobic process, the lactic acid fermentation, as pictured here, you can see there the lactic acid fermentation process. This process generates 2 ATP molecules per 1 molecule of glucose. Not very efficient, right? Only lactic acid fermentation occurs in a human body, however, so it is specific to humans. The only real advantage of using the anaerobic process over the aerobic cellular respiration is that it produces ATP more quickly, so it's useful in emergent situations. So, for example, in the ICU, patients often come in with elevated lactate, and the reason for this is because they're in emergent situations. You know, their lungs aren't functioning correctly, they're in metabolic acidosis, so they're leaning on the lactic acid fermentation system to generate energy. While it's not efficient, it does it quickly, so in this case to prevent death. So then we'll continue this cycle here, and we're going to look at the aerobic process over here in the pink. So now if we discuss the aerobic process, first we'll discuss the conversion of glucose. Discuss the conversion of glucose to pyruvate and then pyruvate to acetyl coenzyme A, which happens inside the mitochondria and generates 2 molecules of NADH. And that I have here again pictured for examples. And now we're going to go into the Krebs cycle and the citric acid cycle, which I've got a couple examples here. So essentially, this is the central metabolic hub. This is the central metabolic hub of the cell. It is also the final common pathway of the oxidation of all fuel molecules, carbohydrates, fats, and amino acids. In addition, this process takes place in the mitochondria as well. It occurs in 2 stages, and here is a simplified version of the process here. This process generates 2 molecules of ATP, 6 molecules of NADH, and 2 molecules of FADH2. So while the Krebs cycle does not generate much ATP, it captures high energy electrons from citrate and its metabolites, through which NADH and FADH2 are formed. And it also facilitates the electron transport chain. So next, I will discuss the oxidative phosphorylation, which is pictured there. This process is a series of energy transformations that includes cellular respiration, the electron transport chain, and proton motive force. Through this process, ATP is formed as a result of the transfer of electrons from NADH or FADH2 to O2 by a series of electron carries. In turn, this generates between 26 and 30 molecules of ATP per glucose. However, this does depend on electron transfer and the electron transport chain, since it consists of proton pumps and a physical link to the citric acid cycle. The oxidative phosphorylation takes place in the inner mitochondrial membrane and depends on, as we stated before, electron transfer and the electron transport chain consisting of proton pumps, and plays a role in the citric acid cycle, which also affects this process. So, in turn, I have this pictured here, which kind of describes a bit of what we kind of just summarized briefly in our final 30 ATP. And then here I've got a little graph that kind of describes also what we just talked about, 25 and 5, which makes the final 30 of our yields. In turn, with all these ideas in mind, the complete oxidation of glucose will yield us about 30 moles, as seen by the graphs that I just displayed to you all. And that is why, through the use of glycolysis, our conversion of pyruvate to acetyl-CoA, coenzyme A, citric acid cycle, oxidative phosphorylation, and ending on that with the Krebs cycle, we get the 30 ATP. So that's my presentation on every step that is involved in generating ATP, FADH2, and NADH, and includes the names, structures, and enzymes for each step. From there, I sought with you all to understand the conversion rates from NADH and FADH2 to ATP, and then to calculate how the 30 ATP are formed. In addition, I included the steps which use an ATP. So, thanks for watching, guys. I appreciate it. I hope you guys learned something.